All right, hey everyone. If you've got a physics exam on the horizon and words like electric fields are making your head spin a little, you are in the perfect spot. We are going to turn that confusion into some serious confidence.
Look, it's totally normal to feel kind of overwhelmed by all these invisible forces and abstract ideas. But that's what this is all about. We're going to break it all down step by step and turn these tricky topics into problems you can actually master. We're in this together.
So here's our game plan. First, we'll crack the electric field itself, how to calculate it. Then we'll get visual and learn how to picture it with field lines. After that, we'll connect it all to potential and energy, wrestle with some of those multi-step problems, and I'll leave you with a formula sheet that's going to be your best friend come exam day.
Okay, let's dive right into our first section. We're starting at the foundation. How do we actually put a number on this invisible thing we call an electric field? You know, a good way to think about an electric field is like an invisible current in a river. The space itself has this property. Now, if you drop a little leaf, that's our test charge, into the river, it gets pushed, right? It moves with a certain strength and in a certain direction. Well, the electric field, E, is just the map of that invisible current. It tells us how strong the push is and which way it's pointing, and that's exactly why it's a vector.
So let's try a typical problem. Let's say we have a tiny charge, an electron, and we know it's feeling a force of 3.2 times 10 to the minus 4 newtons. What's the strength of the field causing that? Well, we start with our main formula, E equals F divided by Q. We just pop in the numbers we know for the force and the charge of an electron. And boom, you get a massive field strength, 2.0 times 10 to the 15 newtons per coulomb. It just shows you how incredibly powerful these forces are on that tiny subatomic scale.
Okay, but what if you don't know the force on a test charge? What if all you know is the charge that's creating the field in the first place? This is way more common. For that, we've got another formula. E equals K times Q divided by R squared. Here, K is just Coulomb's constant. You're going to use that number a lot. Q is the charge creating the field, and R is how far away you are.
Let's try it. We have a 5 microcoulomb charge, and we want to know the field strength a quarter of a meter away. We grab our formula, E equals KQ over R squared. Now, a super common mistake here is forgetting to square the distance R on the bottom, so always double check that. Okay, plug in the numbers, and you get 7.2 times 10 to the 5 newtons per coulomb. And since our source charge, Q, is positive, the field points away from it. Simple as that.
And here's a classic exam trick, right? They'll give you the field and the charge, and then ask you to work backwards to find the distance. Don't let it throw you. It's the same physics, just a little bit of algebra. Let's see how it's done.
Okay, here's a pro tip. Rearrange the formula to solve for what you want before you plug in any numbers. Trust me, it seems like an extra step, but it will save you from so many calculator errors. We start with our E equals KQ over R squared. We do a little shuffle to get R by itself, which gives us the square root of KQ over E. Now it's safe to plug in our numbers. And when we do, we get a distance of 4.24 meters. It's just a much cleaner way to do it.
All right, we've done the math. Now let's build some intuition. I mean, how are you supposed to picture these invisible fields? Well, physicists came up with a great tool for that called electric field lines, and they follow a few really simple rules.
It really just boils down to these 3 rules. Rule 1 is about direction. Lines always flow away from positive charges and point towards negative charges. Rule 2, density tells you the strength. The more crowded and packed together the lines are, the stronger the field is right there. And Rule 3, the big one, field lines can never, ever cross.
And this slide shows that density rule perfectly. Look at the left with the single point charge. See how the lines spread out? They get farther apart? That means the field is getting weaker, which is exactly what our 1 over R squared formula told us. But now look at the right. For a huge infinite plane of charge, the lines are perfectly parallel and evenly spaced. That means the field strength is the same everywhere. It's constant.
So here's a conceptual question you are almost guaranteed to see on a test. We know the rule is that field lines never cross. But why? What's the deep physical reason for that? Just take a second and think about it.
The answer is actually right in the definition of what a field is. A field line tells you the one single direction of the force at that point. So if 2 lines crossed, it would mean that at that exact spot, the force is trying to point in 2 different directions at the same time. And that's just physically impossible. A charge can only get pushed one way at any single instant.
All right, you're doing great. We're ready to add the next layer, which is electric potential.
This is a scalar concept, which means no direction, woohoo, and it's all about energy. You probably know it by its everyday name, voltage.
And this table just lays out the key differences brilliantly. The electric field, E, is a vector. It's about force, and it drops off fast, as 1 over r squared. But electric potential, V, is a scalar, no direction. It's about energy, and it drops off slower, just 1 over r. If you can get this distinction locked in your head, you are way ahead of the game.
So let's run the numbers for a potential. We've got a -4 nanocoulomb charge. The formula is way simpler. V equals Q over R. Notice, no r squared, and because it's a scalar, we don't have to worry about direction. We just plug and chug. And since our charge Q is negative, our potential is also negative, minus 72 volts. That's it.
So what's the big deal with potential? It's our direct link to energy. The work you have to do, or the energy it takes, to move a charge Q through a potential difference V is just W equals Q times V. So to push a 2 microcoulomb charge across a 100-volt gap, it's going to take 2.0 times 10 to the minus 4 joules of work.
Okay, we've got the individual pieces down. But the real test, is whether you can put them all together. Exams just love problems that make you connect the electric field and potential, so let's tackle one.
First, we need the bridge that connects these two worlds. For a uniform field, like the kind you find between two parallel metal plates, there's this beautifully simple formula. The electric field E is just the voltage V divided by the distance d. This little equation is the key to so many of these combined problems.
And here it is, a classic two-parter. A proton gets accelerated by 5,000 volts over 10 centimeters. Step 1, find the field. We use our bridge, E equals V over D. But watch your units. We have to convert 10 centimeters to 0.1 meters. That gives us 50,000 volts per meter. Done. Now for the work. That's even easier. W equals Q times V. We just need the charge of a proton and the voltage they gave us. That gets us 8.0 times 10 to the minus 16 joules. And we've cracked it.
Phew, we have covered a lot. So to bring it all home, here is the one slide you're definitely going to want to pause and screenshot. Think of this as your ultimate cheat sheet for everything we just did.
This table just lays it all out nice and clean. For the electric field, you've got your two main formulas, depending on the situation. Same for electric potential. One connected to energy, one to a source charge. Then your two key relationships for work. And finally, that all-important combined formula for uniform fields. If you know these, you are in really, really good shape.
And that's it. Look, this isn't just random physics for a test. These are the actual rules that run our entire digital world, from the screen on your phone to the processor in your computer. You've just taken a massive step toward really understanding them. So the only question left is, now that you have these tools, what are you going to solve next? Thanks for tuning in.